Hello and good day everybody. So in this video lecture, we would be discussing about how we would be assigning wind loads onto our low-rise structure. So the formula that we will be making use in this procedure would be the following. So it would be given by your equation 207C.6-1 of the National Structural Code of the Philippines. So from that, guys, the value for your P or your pressure P is to be given by this equation. So P is equal to lambda times KZT times P, whereas the value for your lambda is to be your adjustment factor, your KZT is to be your topographic factor, and the value for your P is to be the simplified design wind pressure that is to be given by the table that I will be showing to you later. So same is true with the value for your lambda. So for your lambda and your P, they are to be given by the table that I will be showing to you later. So once again, this is to be the equation that we will be using, and it is to be acting to your structure in this particular manner. So this is to be for your zone A, this is to be for your zone B, this is for zone C, this is for zone D, this is for zone E, F, G, and H. So I'm not quite sure if you can read these values right here, but if you don't, just go to this page, which is page 2-116 of the National Structural Code of the Philippines. So going back here, guys, if this is to be the design wind load that we will be making use, we would still be having minimum loads as defined in this particular section right here of the NSCP. So the minimum pressure for zones A and C, so for zones A and C, the minimum pressures that we will be making use is to be 766 Pascal or 0.766 kilopascal. And for zones B and D, so B and D, the minimum pressure that we will be making use here is to be 0.383 kilopascal. Okay, so those are to be the minimum design wind loads. The limitation of this procedure is that this procedure is only applicable to buildings less than 18 meters in height, to buildings with an importance factor of 1.0, and to structures that is located in an area with an exposure category B, where the respective heights of the surrounding buildings are to be less than or equal to 9 meters in average. So if your structure and the exposure category condition does not conform with the mentioned criteria, you must use a more detailed approach or a more detailed method. So those are to be the limitations that we will be facing using this particular method right here. So what we will be doing here in this video lecture is that we will be solving for the pressures manually using this equation right here, and that we will be applying them in the form of member loads onto our beams using tributary area method. So unlike in our seismic load definitions in the previous video, wherein we have just indicated the parameters in STAAD, and STAAD was the one generating the base shear, in this method, we will be solving for it manually, and then we will be applying it manually once again. So disclaimer everyone that in this particular video, I will only solve for case A right here. As for your case B, you can do it as your own practice problem. Okay, so let's talk about the mentioned criteria first. So for the criteria, so I would just be writing them here. So the first criteria is that your building's height should be less than or equal to 18. And for criteria number 2, the importance factor should be equal to 1.0. And for number 3, this should be having an exposure category B, whereas the height of the surrounding buildings should be less than or equal to 9 meters. So these are to be the criteria that we will be checking. So let's go to the first criteria first. So let's check if our building is to be having a height less than 18 meters. So from the ground floor up, so we would be starting from the ground floor. So node tools, then node to node distance. So I would be getting the node to node distance from your ground floor up until our top floor. And since this is to be a roof deck, so it is 9 meters. So 9 meters is to be less than 18 meters. So this criteria right here is already satisfied. So this is already satisfied. And since if you can remember during the previous pre-recorded video lectures that this building right here is to be a residential building. So looking at the table or the PDF file to your left, it would be having a certain occupancy of standard occupancy. And if you can remember, your standard occupancy has an importance factor of 1.0. So meaning that this criteria right here or this parameter right here is to be true. So for this building, our importance factor is to be 1.0. And as for this number 3 right here, so for exposure category B, once again, looking at the PDF file to your left, if we are to go to this part right here, so exposure category B shall apply where the ground surface roughness as defined by surface roughness B prevails in the upwind direction. So if you would be going to our surface roughness B, so this is to be for your surface roughness B. So it is said here that it is for urban and suburban areas, wooded areas, or other terrain with numerous closely spaced obstruction having the size of single-family dwellings or larger. So in Baguio City, since Baguio City is an urban area and it is also a wooded area, so we would be making use of surface category B. So with such guys, our third parameter right here is already satisfied. So there. Okay, so once again, looking at the PDF file to your left, we would be making use of this particular equation right here. So I would just be writing them to our screen. So the pressure P is to be equal to lambda times KZT times P S30. So for your lambda right here, so let's go check what is to be the value for your lambda. So lambda is to be equal to, so this is to be given by table that I will be showing you right now. So it is to be this particular table right here. So it is to be given by figure 207C.6-1 continued, or the adjustment factor for the building height and exposure. So what is to be the height of our building? So as you can see in this portion right here, it is to be 9 meters. So with such guys, we would be making use of 9 meters. And since this is to be your 9 meters right here, so I'm sorry. So this is to be your 9 meters right here. And it is located at an area with exposure B. So meaning we would be making use of 1.0. So from that guys, our lambda is to be equal to 1.0. So we already have the value for our lambda. And what about for our KZT? So for KZT, we would be going to this particular area in our table. I mean, in our National Structural Code of the Philippines. So this is to be given by chapter 2 page 2-47. So for your value for your KZT, it is to be given by the equation 1 plus K1 times K2 times K3. So if you would be looking at here, so it is indicated here that the value for your KZT is to be equal to KZT is equal to 1 plus K1 plus K2 plus K3, but I think that is erroneous. And the correct formula for KZT is so 1 plus K1 times K2 times K3 squared. So this is to be the correct formula for your KZT. But take note guys that you can only make use of this particular equation if you will be satisfying all of these conditions. So we have 5 conditions. For us to make use of this particular equation right here, all of those 5 criterias must be present. So let's say that if site conditions and locations of structure do not meet all of the conditions shown as specified in this particular section, we would be making use of KZT be equal to 1.0 as indicated in this lower portion right here. And since there are no data given, so we don't have any data about our LH, RH, and whatsoever, we would be making use of KZT be equal to 1.0. So from that, our KZT is to be equal to 1.0 also. And what about for this PS30 right here? So this is to be given by this particular table right here. So it would be given by these tables right here. So as you can see guys, that in this table, our table is to be dependent upon the roof angle in degrees, the basic wind speed, and the zones of our pressure. So this is for zone A, zone B, zone C, zone D, and etc. as per shown in this particular figure. So let's say that if you want to solve for this particular pressure right here, or your zone A, it is to be given by this column right here for zone A. But once again, our table is to be dependent upon the basic wind speed and the roof angle in degrees. So first things first, let's solve for the roof angle in degrees and the basic wind speed first. So as you can see here, so from this particular example right here, it is stated in the previous pre-recorded video lecture that our building is to be having a roof deck and not a sloping roof or not a monoslope roof or whatsoever. So meaning guys that in this example, our roof angle is to be 0 degrees since our roof is to be horizontal. So this is to be the slope of your roofing. So meaning our angle theta, so our angle theta is to be equal to 0 degrees. So that is for our roof angle. So what about for the basic wind speed? So once again, looking at the PDF file to your left, it is to be given by this map right here, or this is to be figure 207A.5-1A, or the basic wind speeds for occupancy category 3, 4, and 5. And if you would be going to this table right here, it is said here that for your occupancy category number 4, which is this one in particular, so all structures housing occupancy or having functions not listed in category 1, 2, 3, and 5. And since the building that we are designing in this example is to be a residential building, thus it belongs to category 4. So we will be making use of this map right here. The next thing that we will be doing is that we will be pinpointing the location of our structure. And since this structure is to be located in Baguio City, so your Baguio City is approximately at this particular location right here, or this location. So zooming in, so if we are to zoom in here, Baguio City is to be located at this portion. So in this part right here. And if you can see this line right here, this is to be having a wind speed of 250. So if you cannot read what I am pointing to you right now, better check your National Structural Code of the Philippines and open it to this figure right here, or figure 207A.5-1A. So there. So this is to be for your Baguio City once again, and it has a wind speed of 250 as indicated here. So from that guys, our wind speed or our velocity is to be equal to 250 kilometers per hour. So we already have our value for our theta and our value for our v. So with such, we can now use the table that I have shown you a while ago, which is this one right here. So this is for your basic wind speed 250, and this is to be for your roof angle. So if I am to zoom this in, we will be making use of this row right here. So since our wind speed is to be 250 and that our roof slope is to be 0 to 5%, or 0 to 5 degrees I should say, we would be making use of this ones right here in the table. So this is for Zone A, this is for Zone B, Zone C, Zone D, and etc. Okay, so what I will be solving for here are the values for our pressure for A, for Zone C, Zone E, F, G, and H. As for your zones B and D, I wouldn't be solving it any longer since our portion at the top is to be horizontal in nature. So I would be explaining to you in detail why solving for your zones B and D are a waste of time. So once again, we would be solving for zones A, C, E, F, and G, H. Okay, so there. Okay, so if you would be looking at the PDF file, so this is for Zone A and Zone C. So I would just be projecting them into our structure. So if we are to look at its front view, so let's say that this is to be its front view. So your Zone A is to be this particular area right here. So this is for your Zone A. And this is for your Zone C. So this is for your zone C. So once again, this is for zone C, and this is for your zone A. So for us to get the pressure for zone A, we would be making use of this particular equation right here. So P is equal to lambda, and our lambda is once again 1.0, and our KZT is 1.0. So 1.0 times 1.0 times the value for your P. And the value for your P is to be given by, once again, this table. So we would be we would be scrolling down up until we go to the basic wind speed 250 and the roof angle of 0 to 5%. So we would be making use of this value right here. And for your zone horizontal pressure for zone A, that is to be given by 1.83. So 1.83. So I will just be writing them here. So 1.83 kilopascals. So there, and with the use of your calculator, since this is just 1.0, your P or A, your PA is now to be equal to 1.83 kilopascal. So that is to be the pressure in this particular area right here. So our pressure here, PA, that is to be 1.83 kilopascals. So what about for zone C? So for zone C, so this is for zone C. So for zone C, the pressure at Z is to be equal to, so lambda times KZT, same old. This is to be 1.0 times 1.0 times the pressure that is to be indicated in the table. So 250, and for our horizontal pressure C, it is to be 1.22, which is this one right here. So 1.22, or this. So with such, so 1 times 1 times 1.22 kilopascal, then this is 1.22 kilopascal. Sorry, this should be PC, not PC. So with such, this is now to be equal to 1.22 kilopascal. So I would just be erasing these parameters right here so that I can tabulate. So from that, guys, our pressure at zone A is to be 1.83 kilopascals. And our pressure for zone C is to be equal to 1.22 kilopascals. So there, I will just be erasing everything first. Okay, so there, so those are to be the pressures that we will be applying in here. But first, let's solve for zones, for the pressures for zone E, zone F, zone G, and zone H. So equals, and equals. And since we are just to multiply it by 1.0 and 1.0, I wouldn't be showing you the solution any longer. So I would just be copying its pressure using the table. So for our PE, so for your PE, where's PE? So it is to be in this location right here. So PE, so that is to be negative 2.2. So negative 2.2 kilopascals. For your F, that is to be equal to negative 1.25. For your PG, this is to be negative 1.53. And for your PH, this is to be your, this should be negative 0.97. And all of them are in terms of kilopascal. So kilopascal. So there. So now that we have already solved for the pressures for each of the zones, the next thing that we will be doing is that we will be converting them into member loads that we will be applying onto our structure. So I would just be once again showing the front view. So if you can remember that this particular portion right here, this is to be for your zone A. And this is to be for your zone C. So this particular area right here from the ground floor up. So the next thing that we will be solving for here is to be the value for this particular dimension right here. And this is to be your value alpha. since you don't know how many meters is to be this dimension right here. And according to this figure, so the value for your alpha, so looking at the PDF file to your left, at this particular portion right here, the value for your alpha is to be 10% of the least horizontal dimension or 0.4 h, whichever is smaller. But they should not be less than either 4% of the horizontal dimension or 0.9 meters. So I would just be solving for them here first. So in this example, so I would just be displaying the whole structure once again. So your horizontal dimensions would be as follows. So it would be this one right here. So this is to be your, oops, sorry. So this is to be for your horizontal dimension or the longer horizontal dimension, and that is to be 12 meters. And the least horizontal dimension is to be 7.8 meters. So 12 meters and 7.8 meters. So self-explanatory that the lower value here is to be 7.8 meters. Your alpha is to be equal to 10% of the least horizontal dimension, or let's say h, or let's say, I think it is better if I would be writing w here, or the width. So 0.1 times the least horizontal dimension or 0.4 times the height of the building, whichever is smaller. And that they should be greater than, so they should be greater than or equal to 4% or 0.04 of your least horizontal dimension, or, and 0.9 meters. So solving for these two right here, so 0.1 times 7.8. Okay, so from our calculator, so 10% of the least horizontal dimension or 7.8, that is to be 0.78. So this is now to be equal to 0.78. And 0.4 times h, so 0.4 or 40% of h, and our h here is to be 9 meters. So 0.4 times 9, this is to be equal to 3.6. So 3.6 meters. So these values right here should be greater than 0.04 W or, and 0.9 meters. So for your 0.04 W, so 0.04 times W or 7.8, 0.312. So this one right here is to be 0.312. So 0.312. So whichever is smaller in this. So as you can see in these two right here, that the smaller dimension here is to be 0.78 meters. But as you can see, this is to be less than 0.9 meters. So with such, guys, the value for RA, so the value for RA that will be governing here is to be 0.9 meters. So there. So this is to be the governing value for our alpha. Okay, but correction, guys, that the value for this dimension right here, so let's say that this is to be your, this is to be the division line between your zones A and C. So let's say that this is to be zone A and this is to be zone C. So if you would look closely to the PDF file to your left, so basically, guys, that this dimension right here is to be 2A and not A. 2 alpha and not alpha. So since our alpha, the alpha that we have solved for earlier is to be equal to 0.9, meaning that this particular dimension right here is to be 1.8 meters and not 0.9. So that is for the division between your load case, your zone A and your zone C. Okay, so since we have already solved for the pressures of the zones, the next thing that we will be doing is that we will be converting these pressures right here into member loads or into line loads. So for us to do that, so I will just be viewing the front view of this. So if this is to be the front view, and if you can remember, we have two zones, two horizontal zones here. So this is to be for your, let's say, zone A, and this is to be for your zone C. So meaning that in this particular area on your left, the pressure here is to be 1.83 kilopascal and the pressure here is to be 1.22 kilopascal. So once again, our goal here is for us to convert this pressure right here into line loads that will act at these members right here. So it would be acting here. So we would be converting it into a line load here. We would also be converting it into a line load here. And we would be converting it into a line load here, as well as for this particular beam right here. Okay, so how can we do that? So the first thing that we will be doing here is that we will be determining the tributary area of each beam. So in here, guys, the tributary area of your top beam is to be this one right here. And the tributary area for your for this particular beam right here is to be this. And the tributary area of the second floor beam is to be this. And the tributary area of the bottom beams is to be this. So from that, guys, so the floor to floor distance of your structure is to be, so I will just be showing it here. So it is to be 3 meters. So meaning that half of this 3 meters is to be 1.5. So from that, this is to be 1.5 meters, 1.5 meters, 1.5 meters, and etc. up until 1.5 meters. So for us to convert this pressure right here into a line load, what we will be doing here is that we will be multiplying this pressure by the tributary width of each of the beams. So for us to get the line load here, at this beam right here, that is basically 1.22 kilopascals times the tributary width. And the tributary width here is to be 1.5 meters. So times 1.5. So looking at the calculator to your right, so I will just be displaying our calculator here. So this is now to be equal to, so 1.22 times 1.5, and our answer here is to be 1.83. So this is now 1.83 kilonewtons per meter, since this is meter, and if you would be multiplying them, since kilopascal is to be kilonewtons per square meter, meters would cancel out and it would give you an answer in kilonewtons per meter. And since this top portion right here has the same tributary width as for your bottom part, this is also 1.83 kilonewtons per meter. So that is for the exterior beams, or the topmost and the bottom beam. So the next thing that we will be solving is for the line load for this particular beam right here. So this one and this one, since both of them has the same tributary area. So the tributary width for this particular beam right here is to be 1.5 meters plus 1.5, or this is to be its tributary width. So 1.5 meters plus 1.5 meters, and that is to be equal to 3 meters. So 3 meters times the pressure, which is 1.22 kilopascal. So 1.22 kilopascal times 3 meters. And looking at the calculator to your right, that is now to be equal to, so 1.22 times 3, and that will give you an answer of 3.66. This is now to be equal to 3.66 kilonewtons per meter. So from that, guys, we will be assigning this magnitudes right here to this portion of the beam right here. So I will just be hiding our calculators first. So I will be hiding the calculators. Then I will be adding your wind loads here. So for the first case, so click add. And looking at the bottom part of your screen, so this is now to be a member load. So member load, and what is to be the magnitude? So the magnitude of this is to be 1.83 kilonewtons per meter and 3.66 kilonewtons per meter. So 1.83. But take note, guys, that since we want our load to be acting along the negative z direction, so from that, guys, I would now be changing this into negative 1.83, and I will be changing the direction here to gz, or the global z direction. Because if I would be pressing gy, our load right here would act vertically downwards. So if I would be pressing gz here, my load would now act towards the negative z direction. So I want that to happen. So I would be clicking add here. And I would once again introduce another magnitude that is to be 3.66 or negative 3.66. So same, I would still want it to be towards the negative global z direction. So GZ, then I will be pressing add. So from that, guys, I now have these two. So I will just be erasing this first. I want this particular loads here to be assigned to this beam right here. So up until this portion right here, from this up until this portion right here, from this up until this, and etc. So I would be applying them here. So the first thing that I will be doing here is that, well, I will be erasing this, and I will go to the isometric view, and I will isolate this portion right here first. So I would be going to the top view. I would be selecting the beams at the front. Then I will be isolating it first. So click view, view selected objects, and from that I would now go to the front view, and I will be assigning this particular loads right here. So from that, guys, I would be choosing the top and the bottom beams at this portion first, and I will be assigning this load right here, which is the one that we have solved for a while ago. So click there, then assign to selected beams. And as for this beams right here, this is for negative 3.66. Then click assign. Assign to selected beam. So assign, then press yes. Then if I would go to the isometric view, this is what it would look like. And so our next procedure here is for us to apply this magnitude at this portion right here. But if you can remember, guys, we would be having a dividing line right here. So this is to be your dividing line. And the one on your left is to be your zone A. And the one on your right is to be zone C. So all of this is to be for your zone C. But take note, guys, that this dimension right here is to be 2 alpha. And your 2 alpha, as per solved for earlier, is to be 1.8 meters. So for the node-to-node distance, guys, so I will just display the node-to-node distance here. So node tools, then node-to-node distance. So the node-to-node distance from this point up until this point is to be 4 meters. So what I would be doing here is that I would be assigning a new, I would be defining a new load. So click add, then go to member load. Then I would be repeating this magnitude. So for the first magnitude, that is to be negative 1.83 along the GZ direction. But this time we will be customizing D1, D2, and D3. So your D1 is to be the starting point of your load, and your D2 is to be the ending point of your load. So that is to be in reference with the start and the end of your beam. So if you can remember, this is to be 1.8 meters. So this is to be 1.8 meters. And if that is to be 1.8 meters, so meaning that this portion right here is to be equal to 2.2 meters, since the total is to be 4 meters. So from that, guys, I would now be repeating what I have been doing a while ago. So I would be clicking add. Then let's go to member load. So this is now to be equal to negative 1.83. Then it is to be acting at the global z direction, and it's D1. So the starting point right now is to be 1.8. And the ending here, so from that, guys, so if you would be starting at 1.8 meters, you would now be ending at 4 meters. So 4. Then I would now be pressing add. So let's try this one. So I would now be assigning this load right here to the top member. So I would be clicking this top member right here. No, I think I should just be assigning it using my cursor, no? So click this, click assign, then I will be clicking here. So as you can see, guys, so I will just be erasing this first. So I now have a load here. But if you can see, guys, we have an error here, since it should end at this particular node right here. So it should be ending here and not here. So our error was brought about by the offset, because if you would be going back here, this D1 right here is to be in reference with the starting point of your beam. And since we have applied offsets before, since we actually had an offset here, so meaning that this particular distance right here, which is 1.8, started from this point. So your 1.8 started from this point, then you went 1.8 here. So this is now to be 1.8 meters and not in this portion. But if you can remember that the node to node distance here is to be 4 meters. So from that itself, we already have an error. So if we are to click on this portion right here, so beam cursor, so if I would be double clicking here, it is said here that the length is now to be equal to 3.6 because if you can remember once again, we have applied a 0.2 offsets here. So 0.2, so this was an offset of 0.2 and this is now to be an offset of 0.2. Thus, making our beam to be 3.6 meters. So what can we do now? So what we would be doing here is that we would be reassigning our D1s and D2 in this particular interface right here. So for us to do that, I would just be erasing everything once again. So if this is to be your beam, so this is to be your new beam, which is 3.6 meters. So an offset was already applied here, so 3.6 meters. And the original, the node to node distance is to be 4 meters. So this is now to be 4 meters. So 4 meters. So if our value for our 2 alpha from this point up until this point is to be equal to 1.8 meters, but we already had an offset here of 0.2 meters. So from this point up until this point is to be equal to 1.8 minus 0.2, thus making it 1.6 meters. So that is now our value for your D1. And as for your D2, since this is to be 1.6, this is now to be, so 1.6 minus 3.6, this is now to be equal to 2 meters. So there. So what are we going to do right here, right now? So click on the load that we have produced. And for our D1, this is now to be equal to 1.6. So our 1.6 is to be from this edge of the beam or the offsetted beam up until that part. So this is to be 1.6 and we will be ending at 3.6 or the whole span of the beam. So 3.6, and if I would be pressing modify, so modify, so as you can see that my load is now this one right here. So from that, guys, I will be assigning this particular beam right here, this particular load right here to this bottom beam. So I would be clicking here, then assign to selected beams. Okay, so there. And as for these two, I would now be pressing a new one. So I would be adding a new one, then member load. Then our magnitude here is to be negative 3.66 kilonewtons per meter. Then it is towards the global Z direction. And same old, our D1 is to be 1.6. And our D2 is to be 3.6. So if I would be pressing add here, then I will be assigning it. So I will be assigning it to selected beams. So there. So as you can see, we now have the loads for your zone C. So that is for your zone C. So let's solve for the magnitudes for the member loads for your zone A. So I would go once again to the front view. So this is to be your front view. And once again, I would just be erasing this. Okay, so this is for your zone A. So this one right here is for your zone A. And according to this value right here, the pressure for your zone A is to be 1.83 kilopascal. So for us to determine the line loads here, so that is basically the pressure times the tributary width. And we have already defined them earlier, that the tributary width of this beam right here, so this is to be its tributary width, that is to be 1.5 plus 1.5, so that is basically 3. So same is true with this second floor beam. So this is to be 1.5, 1.5, and this is to be 1.5, and this is also 1.5. So from that, guys, for us to solve for the line load here, this is now to be equal to 1.83 kilopascals times 3 meters, or the tributary width, giving us an answer of, so looking at the calculator to your right, so this is now to be equal to 1.83 times 3. So this is now to be equal to 5.49. So 5.49 kilonewtons per meter. So that is for these two right here. So this is for your third floor and your second floor beams. So for your roof deck beam and for your first floor beam, they are to be given by, so this is now to be equal to, since this is to be your tributary area, this is to be 1.83 kilopascals times 1.5 meters, since this is to be its tributary width. So we would be arriving at an answer of, so looking once again to the calculator to your left, this would be 1.83 times 1.5. So we would be arriving at an answer of 2.745. So 2.745 kilonewtons per meter. So from that, guys, we would be assigning them here. So add, click add, then go to member load. Then for W1, that is now to be equal to negative 2.745. So this is for this top beam and for the bottom beam. So this is now to be acting at the global Z direction. But take note once again that we need to have a value for your D1 and your D2, since we are only applying it in a fractional part of a certain beam. So from that, guys, if you can remember once again that if this is to be 3.6, so this is to be the new dimension of the beam considering the offset. So this is to be 3.6. Wait, I think it is better if I would be enlarging it. So let's say that this is to be your new beam. So this is to be an exaggerated size of it. So this is to be 3.6 meters. And the original node-to-node distance is to be 4 meters. So this is to be 4 meters. And for your 2 alpha, which is 1.8, it should be measured from node up until node. So node to node. So this is now to be equal to 1.8 meters. So from that, guys, so if this is 1.8, this one right here once again is to be 0.2, since we have already applied 0.2 offset before. So from that, from this point up until this point, this is now to be equal to 1.6 meters. And this is now to be equal to 2 meters. So taking those into consideration, our D1 right here is to be 0, since our load would be starting here. So our load would be starting here. I'm sorry. So our load would be starting here. And it should end here. So it should end here. So meaning that our D1 is to be 0. So that is to be the starting point. And the end point should be 1.6, since it would be ending at this portion. So I have already clicked add. And as for the second magnitude, so this is for the interior beam. So this is now to be equal to negative 5.49 kilonewtons per meter. So I would be clicking add, close. Then I would now be assigning them onto our structure. So there. And I would now be assigning this. So the one with the smaller magnitude would be assigned here. So I would be clicking assign. And the ones that the ones that have a greater magnitude would be applied to the interior beams. So it would be this one right here. So assign to selected beams, then press yes. Okay, so if we would be displaying the whole structure, this is what the load would look like. So there, as you can see, these ones right here are for your zones A. So these two right here are for your zone A. And for all of this is for your zone C. As you can see, your zone A would be having a greater magnitude than that of your zone C. So that is for our wind load case number 1. But what about for our wind load case number 2? So for our wind load case number 2, it is basically the reverse of your wind load case number 1. So what do I mean there? So earlier we have assumed that the zone A or the A zone of our member is to be located here, and the zone C of our structure is to be located here. But this time, for our second load case, we would be locating our load in this portion right here, or our zone A at this portion right here, and we would now be assuming that the zone C is to be located at this portion right here. So what I would be doing is that I will be copying these magnitudes. So I would be copying these magnitudes right here, and I would be pasting them here at WZ2. But this time, I will be reversing the load assignments. So once again, the ones on your left is now to be for your zone C. And the ones on your right is to be for your zone A. So it would be as simple as that. So if you can remember, guys, that I have told you earlier that I would not be solving for zones B and D anymore because your zones B and D would be acting here. So your zones B and D would now be acting at this portion. So this is for your zone B, and this is for your zone D. And as you can see, we don't have a tributary area here. But let's say that we would be having a certain sloping roof. So sloping roof would be having a certain vertical component. So let's say that this is to be its vertical projection, I should say. So this vertical projection is now your tributary area. But since once again that we wouldn't be having a certain roof here, since this is to be a roof deck, it is a waste of time for us to solve for PB and PD since our tributary area for PB and PD is to be 0. Those are to be the reasons why we did not include the computations for PB and PD. Okay, so there. So as you can see here, PA, PC, PE, F, G, and H. So B and D are missing. Okay, so anyway, so I would now be reassigning these loads right here to WZ2. So I would just be fast forwarding it. Okay, so since we have already assigned this particular loads right here, so the next thing that we will be doing is that once again, we will be assigning partial loads in these members right here. So once again, if you can remember, this is, the node-to-node distance here is to be 4 meters, but we have already applied an offset of 0.2 meters in both sides. So from 4 meters, so this is to be 4 meters, which is the node-to-node distance, and our new beam given by the offset is to be 3.6 meters. So I would just be erasing this and I would be exaggerating our drawing once again. So this is to be 4 meters and this is to be 3.6 meters. So if this is to be 4 meters and this is to be 3.6 meters, so your alpha now is to be equal to, your 2 alpha is to be 1.8. So from this point up until this point, so this is to be 1.8 meters. So from that, guys, if this is to be 1.8 meters, since we already have a 0.2 meter offset here, this is now to be equal to 1.6 meters. So if this is to be 1.6 meters, meaning that this one right here is to be 2 meters. And since this is to be our starting node and this is to be our ending node, the next thing that we will be doing here is that when we are to apply a certain load for your zone C, so for your zone C, if you can remember that our magnitude here is to be equal to negative 1.83 and negative 3.66. But this time, our D1 is to be 0 since this is to be your starting point. And your D2 is to be 2 meters. So from 0 up until 2 meters. So I would be pressing add. So same is true with our negative 3.66. Then press add once again. So I would just be applying them. So this is for your negative 1.83. So this one right here. So this is for your negative 1.83. Oops, I'm sorry. Take note guys that you should be directing it to the global Z direction. So if you would be directing it to the global Y direction, this is what would happen. So this is erroneous. So I will be double clicking here and I will be changing its direction to global Z direction. Then click modify. So there. And for your negative 3.66, so GZ, modify, close, and I will be assigning them here. So assign to selected beams, then click assign. So those are to be our loads for zone C. So for zone A, so if this is to be our starting point right here, so once again, this is to be for our zone A. So from that, our starting point is now equal to 2 meters. So this is our starting point and it would end at 3.6. So from that, guys, I would now be adding another one here. So click add. Then member load. So what is to be the magnitude of your zone A? So that is to be negative 2.745 as solved for earlier. Then GZ or the global Z direction. So for D1, this is to be equal to 2. So your starting point is 2 meters from your starting node. So 2 and it would end at 3.6. Then click add. So that is for your exterior beams, and for your interior beams, this is to be 5.49. Then click add. Okay, so there, and I would be assigning those to these beams right here. So this is for negative 2.745. This is for negative 5.49. And this is for negative 2.745. So from that, guys, our zone A in this load case is to be this one, and our zone C is to be this one. So that is for our second load wind case. So once again, for your first load wind case, your zone A is to be on your left, and for your second load case, your zone A is to be on the right. So it would be as simple as that. So for your wind load case 3 and 4, it is to be very similar to this. It is just that aside from assigning it at this portion on your, in front of you, your load would now, your wind load would now act at the back walls or the rear walls. So it would be this one. So this one right here. So view selected objects. Then voila. So if I want to view its isometric view, it would look like this. So this is for your frame at the rear part of your building. So what I would be doing is that I would be reassigning this. So this loads right here. But this time, I would be assigning them to the beams at the back. Okay, so now I am already done in assigning my wind loads in the front and the rear portion of my building. So if I am to display the whole structure, so this is the whole structure itself. This is for the first case, which is located at the front portion of the building. This is for the second case, so same. Front portion of the building, it's just that your zone A and C are interchanged. And this is for your rear portion of the building, and this is for the other rear portion of the building. Whereas your zones A and zones zones A and zone C were interchanged. So the question is, are we done? So, oops, I think I have an error here. So we have a certain error here. So this particular member right here should not be here. So I would just be deleting this. Okay. So there, and the next thing that we will be doing is that we will be assigning this particular pressures right here. So if you would be looking at the left portion of your screen or this PDF file, so this is for your E or your pressure E, pressure F, pressure G, and pressure H. So we will be assigning them. But as you can see guys, that these pressures right here are negative. So meaning that these particular pressures right here are suction in nature or suction pressure. So meaning that if they are to be vertical pressures, they would be acting vertically upwards because they are, I'm sorry for the term, but they are practically sucking the top portion of our building. So I can't think of a better term, or vacuuming or whatsoever. So that is to be the case. So what I will be doing right here right now is that I will be isolating the top view once again. So I will be going to the front view, then I will be isolating this, so view selected objects, and I would be going to the top view. So with such, I will now be assigning this pressures right here. So this is for this portion. So this is for your PE. This is for your PF. Oops, I'm sorry. This is for your PE. This is for your PF. This is for your PG. So this is for your PG. And this is for your pH. So wait, so this is for your pH. So we have two approaches. It is either that we will be applying this. So we will be applying this particular pressures right here as a floor load, but we can only do that if your frames, or let's say your beams, is to be exactly oriented like this. So this is to be your beams. This is to be your beam, 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 and beam. So if this is to be the case, you can actually assign floor loads here. But the thing is, we don't have this geometry of our roof beams. So what we will be doing once again is that we will be converting these pressures right here into line loads once again, or member loads. So with such, so this is to be our beam. This is to be our beam, beam, and beam. But I would be writing our pressures here first. So our pressure at this portion, or our PF, this is to be negative 1.25. At this portion, this is to be negative 2.2. This is to be negative 1.53. And this is to be negative 0.97. Okay, so for the line load here, so this is now to be equal to what is to be the tributary width. So the tributary width here would be at this location. So I will just be displaying our node to node distance first. So utilities, node tools, then node to node distance. So this is to be 3 meters. This is to be 1.8 meters, and this is to be 3 meters. So I would be erasing them first. So this is to be it. So 1.8, 1.53, and whatsoever. So I will just be dividing this once again. So this is to be the division between your zone E and F to G and H. And this once again is to be 2 alpha, or 1.8 meters. Okay, so anyway, solving for our line load. So the tributary width of this particular beam right here is to be half of 1.5. Half of 3 meters. So this is now to be equal to 3 meters divided by 2, and that is now to be equal to 1.5 meters. So same is true with this one right here. So this is 1.5 meters. And what is to be half of 1.8? So from that, if this is 1.8, this is now to be 0.9 and 0.9. Then same is true with this. This is now to be equal to. So this is to be 1.5 and 1.5 respectively. So with such, for our load, line load in this portion right here, this is to be equal to, so negative 1.53 times 1.5. So looking at the calculator there, so that is basically equal to, so negative 1.53 times 1.5. So enter negative 2.295. So with such, this is now to be equal to negative 2.295. So that is for this particular beam right here. And for this for the second beam. So for this beam right here, if you can remember, our dividing line for our pressure earlier is to be this one. So this is to be our dividing line. So our tributary area for this particular beam is to be 1.5 plus 0.9. So looking once again at the calculator, so 1.5 plus 0.9, that is to be 2.4. And we will be multiplying that by our pressure of negative 1.53. So with such, our value here, so line load here, that is now to be equal to negative 3.672. So negative 3.672 kilonewtons per meter. So those are to be for this portion. So I will just be erasing this. So there. So 3.672 and 2.295. So what about for this particular beam right here? So its tributary width is to be 1.5. So half of 3 meters and half of 1.8. So 3.5 plus 1.8 divided by 2. So that is basically, so 0.9. So 1.5 plus 0.9, that is also 2.5. I mean 2.4, I should say. So from that, we will be multiplying 2.4 by our pressure. And our pressure here is to be negative 0.97. So negative 0.97, enter. And our line load here is now to be equal to negative 2.328. So negative 2.328 kilonewtons per meter. So that is for this portion. And as for this last beam right here, this is to be 0.97 times 1.5. And this is now to be equal to, so 0.97 times 1.5. So that is to be 1.455. So 1.455 negative, I should say, kilonewtons per meter. Okay, so before solving for this portion, what I would be doing here is that I would be assigning this first. And since in this setup right here, so as you can see this setup right here, that your value for your zone E and F is to be at the left side. So looking at the upper left corner of your screen, so that is basically that case A. So meaning that in this portion right here, this is to be zone A. So zone A, and this one right here is to be your zone C. So meaning that this is for wind load case number 1. So from that, guys, I would now be clicking wind Z1 or WZ1 here, and I will be clicking add. Then I looking at the top portion of your screen. So I would be going to member load. Then I will be assigning, so negative 2.295 first, but I would be assigning it as positive since a negative value of pressure means suction or vacuum. So meaning that it is going vertically upwards. So from that, if it is going vertically upwards, so it is now to be positive on your global Y direction. So I will be clicking add here. So what else? We also have 3.672. So 3.672. We'll be clicking add. Then I also have 2.328. So 2.328. We'll be clicking add. And I also have negative 1.455 or 1.455. So I'm sorry, I forgot to hide my calculator. So let's hide the calculator first. So once again, guys, that earlier I have assigned these loads right here in our load case number 1. Since in our load case number 1, that is the case wherein the location of your A or the location of your zone A is to be in the left side. So that is to be true with this. So from that, I will just be erasing everything first. Okay, so for your uniform global Y direction, so for this 2.295 right here, this is to be acting at this beams right here. So what I would be doing is that I would be assigning them, of course. So let's use cursor to assign. So I would be clicking here and here. Then for this, click here, here, and here. For this, I would be clicking here. And for this, I would be clicking here. So that is for this portion right here. But take note that, guys, that we also need to assign them at this particular portion right here. Same old. What we would be doing is that we would be adding another ones here. So click add. Then go to member load. So I would be going to member load here. Then, so uniform force and our W1. So I would just be copying this. So 2.295. So positive 2.295. But our D1 is to be 1.6 up until 3.6. So why is this the case? It is because in this particular portion, so from your 3-meter line right here up until this portion, this is to be 1.6. And from this portion or your starting portion up until your end, that is to be 3.6. Up until this point. So from that, guys, 1.6 and 3.6. So that is for 2.295. And for the next, so this is for the second one, so 3.672. So what I am actually doing is that I am just copying these ones right here. So 3.672, then 2.328, then 1.455, then add. Okay, so I would just be erasing all of this first. And I will be assigning the loads that I have computed. So for this one right here, so for this one right here, I would be assigning it at this portion. For this one right here, I would be assigning it to this portion. Oops, I'm sorry. Okay, so I'm correct. So as for this one right here, I will be assigning it to this portion. Or did I? So as for this one right here, I am to assign it to this portion. So I think I am missing something. Oops. So this should be assigned here. This should be assigned here. And this should be assigned here. And this should be assigned here. So from that, I will just be deleting this one. So okay, so there. So the last thing that we need here is for your zones E and F. So if I am once again going to the top view, so I would just be selecting this, then view selected object, and I would be going to the top view. So I am missing our zone right here, or our zone E and F. So once again, for your zone E, it would be this. Sorry. So this is to be the dividing line, and this is to be the dividing line once again. So this is for your zone E, and this is to be your zone F. So for your zone E, this is to be negative 2.2, and for your zone F, this is to be negative 1.25. So for the load here, this is basically equal to, so negative 2.2 times the tributary width, and the tributary width here is to be 1.5, since that is to be half of 3. And for this particular beam right here, our tributary area here, our tributary width here is to be half of 1.8 and half of 3. So that is to be 0.9 and 1.5. So the total here is to be equal to 2.4. So same is true with this portion right here at the top. It's just that for your zone F, your pressure is to be equal to negative 1.25 kilopascal. So there's what I am going to do right now is that I would be computing their line loads. So looking at the calculator on your right, So for negative 2.2 times 1.5, this is now to be equal to negative 3.3. So this is to be negative 3.3 kilonewtons per meter. And as for this beam right here, so for this portion right here, this is to be equal to 2.4 times 2.2. So that is to be equal to negative 5.28. So negative 5.28. And for this beam, this is to be equal to, by the way, kilonewtons per meter. So for this beam, that is basically 2.4 times, so by the way, 2.4 times what is to be the pressure of PF, negative 1.25. So answer there is to be negative 3. So negative 3. And for this beam right here, this is basically negative 1.25 times 1.5. And this is to be equal to, so negative 1.25 times 1.5. So this is once again equal to negative 1.875. So negative 1.875 kilonewtons per meter. So highlighting them, these are to be our answers. So this one, this one, this one, and this one. So I would just be assigning them into our load case details. So I would be hiding our calculators, then I would be pressing here, WZ1, then I would be clicking add. Then I would go to member load. So for this one right here, so negative 3.3. So positive. So this is now to be positive since it is directed vertically upward. So GY, and our D1 here is to be, so 1.6. So this is to be 1.6, and this is to be 3.6. So you should have mastered this already by now. So once again, it came from this point. So from this point up until this point, that is to be 1.6. And from this point up until this point, this is now to be 3.6. 2 meters. So from the starting point up until the end point, that is to be 3.6. So I'm sorry if I am blocking the way. So this is to be it. So this is for the first one. So negative 3.3. Then click add. Then for the second one, that is to be 5.28, which is this. So 5.28. Click add. Then for this, for the next one, that is to be 3. Click add. And for the last one, that is to be negative 1.875 or 1.875. Then click add. Okay, so I would just be deleting everything right now. So for us to have a clear plan, so I would just be assigning this. So assign cursor to assign. I would be assigning it here. Then I would be assigning this one right here to this one here, and this one here. So from that, if I am to look at my whole structure, these are to be your, so this should not be 1.6 and 3.6. This should be 0 up until 1.6, I should say. As well as this. So you would be starting from 0 to 1.6. I'm sorry about that. So there, and 0 to 1.6. Then as for this is to be 0 up until 1.6. Then modify. So those are to be it. So take note, guys, that this is only for the first load case. And for the second load case, what you would be doing in the vertical pressures is that you would once again be reversing it, just like what we did here in the horizontal projections. So I wouldn't be doing that any longer. So you can solve for it for your practice problems. But basically, this is how we would be using this equation, or using equation 207C.6-1. So that's it for this video. See you again soon.